My name is Jason Chen. I am a program manager here at AFWERX. Thank you for joining us today, and thank you for joining us on the first day of Fusion. You've joined the workshop, and the workshop title for this workshop is Enhancing COVID and Overall Base Resiliency via Simple HVAC Systems. With me is Scott Duncan, Scott with one T, by the way, from Conservant Systems. And also Jeff Cool, manufacturing partner for Conservant Systems. So welcome. We will get started. Scott has a presentation up, so if you could take a look at your screens. We will get underway very shortly. We are taking questions, so if you have any questions, please use the chat feature. I've been surfacing some notifications to you over chat. If you could type your questions in the chat, I will politely interrupt Scott during his presentation to surface your questions and ask him. Otherwise, we will get started. We have about 25 minutes for the workshop. So Scott, why don't you take it away?
Cool. Well, thank you so much, and thank everybody for being here. I really appreciate your patience. So I'm going to be talking about HVAC systems and how they can either help or hurt the base of the future and our warfighters. And basically, we're going to be talking about how existing systems, HVAC systems, can actually hurt resiliency. They grow mold. They can spread microtoxins around. They're really good at spreading COVID-sized particles around buildings really fast. I'm also going to talk about how we've developed a technology for the Corps of Engineers that can cut relative humidity control energy by 57%. And then by augmenting it, we can get a capture or kill rate for about 99.999% of the COVID-sized particles that get spread around inside buildings. And that's compared to like a hospital operating room requirement of like 75 to 84%, just to kind of put that into perspective. So really good filtration and UVC kill. And then also we want to talk about how do we turn HVAC systems into a low maintenance asset instead of being essentially an impossible HVAC, liability nightmare for the maintenance team, because the bases basically don't have enough money to maintain all these complicated systems that are out there, and so a lot of them fail, right? So also feel free to visit our showcase. It's in the resiliency area, and then it's other resiliency. Just look up Conservant Systems. So this is a version of a topic that we gave to the NAVFAC global engineering crews about 2 weeks ago, and it was anywhere from 2 hours to 2 hours 40 minutes, depending on which part of the world we were talking to. So we're going to shrink that way, way, way down. So we're going to talk really fast. But again, if you got questions on this, we can connect outside of this, either at the showcases or just, we can do webinars for you guys personally. So really quickly. So this is just a quick discussion. It's not professional advice that you need to go build your building this way. Don't do that. You got to get a PE involved to do that. With viruses and other pathogens, HVAC systems are a big part of the problem. They don't and they can't control relative humidity properly. They have crummy air filters. That's a technical term, crummy. They're not equipped with UVC to kill things. They're super energy intensive, and they require a lot of maintenance and a lot of funding, which the bases typically don't have. A lot of them are very failure prone, and they actually cause mold growth and corrosion. Originally, I wasn't targeting corrosion because I just, the way we created this thing was I was on Corps of Engineers or Army bases, and I just kept on finding mold in the buildings. And the DPW guys were doing everything they possibly could, but it kept on being traced back to the air conditioning system. We're actually creating the conditions that could grow mold. So that's the problem. The air conditioning systems were just too maintenance intensive, and they were designed basically to grow mushrooms. So what is HEADS? HEADS is the high efficiency dehumidification system. It's a super simple design. That's the idea. It has to be super simple to be able to be maintained on the bases. So here's kind of a little bit of background. To properly control relative humidity, you need to subcool the air way down to condense moisture out of it. Then you have to heat the air back up. If you don't heat the air back up, you are going to end up with mold growth. You're going to have high condensation in the facilities, and condensation in the facilities, which grows mold. And a lot of the alternatives that are out there are super complex and very failure and maintenance prone. And that's because energy codes have now required everybody to use energy recovery for reheat, because reheat is a really energy intensive process. So that's part of the problem. So I already went through this, why was HEADS created, solve energy waste and mold growth problems. Here's a quote from the Corps of Engineers chief engineer. Biggest problems are systems are way too complex and they break. That's basically his quote. So when they fail, we end up with mold and corrosion. This is just the ASHRAE president saying the same thing. Everything is too complex. And my thought on this is if an engineer had to operate and maintain the first HVAC system they ever designed for a year, the rest of their designs would be completely different. So if they had to maintain something that they designed, it would be a lot different world right now. Going back to this, complex systems fail. The bases just don't have the manpower or the funding to keep complex systems running. ASHRAE 62.1 now requires buildings to be run 24/7 when you have when it's humid outside, a dew point of 60 degrees or higher. So it's going to really, really ramp up the energy intensity of most buildings. We anticipated this several years ago because we saw moldy buildings when they were being shut down. So HEADS actually addresses this really energy efficiently. So I'm going to skip to the next bigger one. So this is how simple HEADS is. So this is a replication of an air handling system. Starting on the left-hand side, you've got 95% to 99.999% air filter banks. Again, versus like a normal air conditioning system is a 20% effective filter bank. Hospital OR requirements are typically in that 75 to 84% range. So the 95% is our normal off-the-shelf. We would put that on any base anywhere. That goes anywhere. For more critical applications, we've got the 99.999% version of it, and then UVC also.
Hey,
so here's
Scott.
how it works. Yes, sir.
We've got a question from Justin.
Sure. Okay.
What size pathogens will it deactivate?
So it goes down to the submicron. Like I think it's down to like 0.1 micron is the filtration level that we can get down to. And then the UVC, ultraviolet light, that's just UVC is a combination of power, like wattage power, plus contact time. So that's a great question because one of the things we do is we slow the air way down inside this unit. So we're running like 200 to 300 feet per minute through the unit velocity versus most air handlers are in the 550 to 600 feet per minute, 500 feet per minute range. So by slowing the air way down, the UVC has much greater contact time. So the contact time is direct proportion to the kill time, kill effectiveness. So the slower the air is going through that thing, the better the air filters work, which is one thing that NASA has proven. And also the UVC has a much greater chance of killing things. Even though viruses aren't really alive, it quote unquote kills them. Right?
So is there an ideal contact time for UVC?
Gosh, I like to see, I call it effective contact time, but several seconds. In a normal air conditioning system, you're looking at a quarter of a second or 0.4 seconds of contact time. We like to use additional lamps, get the intensity up, and we can also add another bank of UV lights in different places. UV lights are really cheap, but you have to watch out for UV lights because they're very aggressive. Like they will eat wiring. They will eat like rubber, the rubber on the fan belts, right, for the motors and the motor drive. They will totally kill anything that isn't protected, right? So loading things up with UV is great, but you got to protect the system from the UV.
Okay, thank you.
Great question, thanks. So here's what we do. We take these really great filters, we blow the air through, we use a fan wall type technology, so we have multiple fans and they're all direct drive, variable speed ECM motors. So we always have an N+1 setup, so if one fan dies, the other fans will speed up slightly and pick up the slack. So we blow this hot, wet air through a cooling coil. We come out the other side of the cooling coil with really dried out, well, it's like 100% relative humidity air, but it's very low moisture content, right? So it's very cold. 48 to 57 degrees is typically the temperatures coming out of here. And then you have to heat that air back up, right? Because this air, in point number 3, that's 100% relative humidity and really cold. So again, you have to heat that air back up using a reheat coil before you send it out into the ductwork and into the building. So how do we do that? So we use a much differently designed cooling coil. So air velocity is much lower. We have much greater contact time between the air and the coil. Like a normal 4-row coil, the air blasts through that in like 6/100ths of a second. Think about that. You're trying to do all of your air conditioning and dehumidification in 6/100ths of a second, okay? The blink of an eye is 0.3 to 0.4 seconds. So we slow the air way down. We're at the 0.24 to 0.36 seconds. air to coil contact time. We have added drain fans to get the condensate out of the system, but all kinds of cool stuff happening here. Sorry, I'm talking so fast. So we come out the backside of this cooling coil with 70-degree chill water return temperatures instead of the normal 52 to 55-degree chill water return temperatures. That is warm enough to act as a reheat energy source. This was so simple, it took 4 years to get it patented. 4 years to go through this process to get it patented because it was too simple. But what happened? We did 70-degree water, we got 50-degree air, call it. I got to heat this air back up to 55 degrees, or on light low days, you might be heating it up to 65 degrees. So I dumped some of this warm water into my energy recovery coil. This is acting as my heating coil, okay? If I take 50-degree air, I heat it up to 55 or 60 or 65. I'm also taking this 70-degree water down to 62 or 58 or 55 degrees, depending on how cold this air is. So I'm taking BTUs out of the chill water return before it goes back to the chiller plant. So in this case, I'm saving about 30% of my cooling load because I'm taking heat out of the water before it goes back to the chiller plant, right? If I used 1 million BTUs of reheat, I cut 1 million BTUs out of my chiller plant load. So this might be 4 million BTUs plus 1 million BTUs in a normal system. In the head system, it's 4 million BTUs minus 1 million BTUs, right? So instead of being a 5 million BTU load at the coil, we're a 3 million BTU load at the coil. So it's really massive energy saving. That's how simple it is. No rotating parts, nothing to fail. I mean, everything fails eventually, right? But nothing that's going to require belt drives or normal maintenance or anything like that. So with that, is there any questions on this one? Because this is kind of the heart of the technology. So this next slide, when you guys actually, when you get a download of this thing, this one has all the text on it that just describes what I just went through. So you don't have to, I guess I should have put this one first so you didn't have to speed read and listen to me that fast. So this is more of a discussion on how we build the unit, like 73% heat transfer fins, epoxy coated coils, all that stuff. We built these things Guam tough. We worked with NAVFAC Marianas and we worked with Naval Air Station Key West to determine what they felt would work on their bases, because those are two of the harshest places on the planet as far as salt air and hot, humid, all the time weather. So we worked with them really closely to develop that. This next slide is just talking about, here's a bunch of different ways that heads solves HVAC caused mold growth. There's over 75 ways that HVAC systems cause mold growth and corrosion. Over 75 ways. So it's really bad how air conditioning systems can do this, and we want to solve as many problems as we can. This slide is just from the Corps of Engineers testing that was done with the Environmental Security Technology Certification Program. The minimum savings on this right column was about 57%, and higher savings was over 70% savings for like admin buildings and training facilities and stuff like that. So really big energy savings and really simple, right? So this page just describes the kind of the savings table. So again, when you go back to it, you'll be able to read this and you'll see what I just said. So here we get into the antiviral version of it. So like I was saying, the normal heads version is a 95% capture or kill rate. And the antiviral version for like more critical facilities is 99.999 or above. We can just add more filters basically. And again, this is in comparison to the 75 to 84% requirement for most hospital operating rooms. So even our standard 95% unit is way better than the hospital operating rooms are required to have, which was kind of scary to me when I found that out. Goodness gracious. So how do we do it? Again, this is just a lot of text, but again, you can, when you get the download of this, we can go through it, or we can just present to you as well. I'm not going to read all these things, but it's just a lot of cool things that we did. So this is a diagram of where viruses and bacteria like it. Anywhere it's red, like high relative humidity or low relative humidity, that's where viruses and bacteria like it. So we're trying to keep the heads in this 40 to 60% relative humidity range. So not only do we set up heads units to dehumidify, which is a huge energy consumer saver, we set up to humidify in the winter, or like in California, we get what we call Santa Ana winds, where it's 105 degrees and 4% relative humidity, right? So we want to keep these buildings in this range to hurt the viruses and hurt the bacteria and stuff like that. This is a quick flow chart on how heads does it. Again, I'm not going to go through this in a lot of detail, but suffice to say, we use a lot of really great filters. and a lot of UV, and properly placed UV with low air velocities and stuff like that. This chart, this table basically talks about, in the left-hand column, your standard HVAC units versus hospitals versus standard heads units versus the antiviral version of head. So the next page talks about the notes that go along with that. This was a situation that came up a while back, is how do you create existing buildings into healthcare facilities, right? HVAC is a really big deal. If you're trying to put 6 people into a building, you have to add a ton of UV, and you have to add filters. And when you add filters, you hurt the air pressure drop, and you hurt the airflow rates, and all kinds of things happen. So, HVAC can be a really big problem when you're trying to convert an existing building to be a healthcare facility, or even portable hospitals, like the 10 hospitals and stuff like that. A lot of them were built just with normal DX systems, which they were built that way because it was fast, it was expedient, but that's not the right way to do it because they didn't have the air filters you needed, the air changes needed, stuff like that. So this is a topic that came up a while back. Short-term emergency thoughts when you have little or no time to prepare for an influx of COVID patients. So the right thing to do is to put in the right HVAC systems or augment your existing systems. Like, we can use heads to augment the existing facility, right? You don't have to rip out and replace every single air handler in the building. You can augment it. Like what we're doing on a lot of AFWERX facilities right now is putting these in as the fresh air systems, the dedicated outdoor air systems, because the existing systems out there are failed. We chatted a little bit earlier. Actually, I don't think anyone was online when Jason and Jeff and I were chatting, but Jeff has been on a base recently, and he looked at 21 barracks. There was over 40 dedicated outdoor air systems. These buildings were like 10 years old. 100% of the 100% of the dedicated outdoor air systems were failed. So you got a single point failure. It has to be reliable, and they build these things so complex now with all these energy recovery wheels and all this other stuff. It just becomes a maintenance nightmare that the bases just can't handle because they don't have the staff. Like at Bragg, one guy was taking care of 82 buildings. He can't take care of 82 buildings. That's just impossible. The guy is down at Naval Air Station Key West. He has 45% vacancies in his maintenance staff. That means 45% of the people he's allowed to have, he doesn't have. And he was probably understaffed by 50% to begin with. So having these super complicated systems that kind of seem simple on their face, but when you dig a little bit deeper on the amount of maintenance they require, it's a real problem. So anyway, the heads units, high efficiency dehumidification systems, the 95% version and the 99999, they can ship in 6 to 8 weeks. So if you have a situation where you have a little bit of time, these things can go in again to augment, or if you have existing systems that need to be replaced, you can replace them pretty quickly. So if you don't have time to do that though, so we were faced with a situation where one of the military branches was expecting like literally hundreds of COVID patients into one of their facilities. What could they get done by this weekend? Okay, so obviously we're not going to ship, 8 weeks out. It's not going to solve the problem for this weekend, right?
Scott,
So,
this is Sandeep. Can you hear me?
Yes, I have you.
Yeah, I had a question. I joined a little bit late. For overlaying the solution, what's the prerequisite? As you mentioned, the buildings are, again, over the last 30, 40 years, they've got so many variations in technology and how they are operated.
Yeah.
What are the 1 or 2 critical prerequisites that must be there? And that's all you need, the dependencies.
So the biggest one that makes it the most cost effective, if it's a chilled water based system. So if you have a chiller and you have chill water piping available, that makes it the most cost effective. But we're looking at other facilities that are DX based, and many direct expansion DX systems. They don't have the ability to properly control relative humidity. But rather than ripping out and replacing the entire system, what we propose doing is putting like you can literally have these little tiny 5-ton packaged chiller plants, right? One facility we looked at was 2,000 square foot guest entry point to a base, right? And it was just full of mold. It was 3-4 years old. It was full of mold. And the first thing these people see when they walk on the base is a moldy facility. That's not good. So the idea was we put a little 4-ton packaged chiller with a heads unit that preconditioned all of the fresh air. So then we just ran, the idea was, we haven't done it yet. But the idea is you just run pre-dehumidified air into these little DX systems. They were actually VRF systems, but you pre-dehumidify the air so that as the compressors are cycling on and off for the DX systems, you're not dehumidifying, rehumidifying, dehumidifying, rehumidifying. So basically just precondition the air to make it work. So that was much more cost effective than ripping out the entire HVAC system and putting a chill water based system in, right?
Okay.
So thank you for the question. Great question. So, so this is the, if you don't have time to do anything, here's what you can do, right? This was my thoughts. This is what was presented to the, this particular branch of the military. So load up on UVC lights. I mentioned earlier, but some people might not have been here, UV lights are great, and the longer the contact time, the better, and the more power, the better, and they're relatively cheap. But you have to watch out for, like, here's my little caveat here. This is a short-term deal. The amount of UVC can actually kill your air handler as fast as, not as fast, but it can kill your air handler really quickly because the UVC is so intense, it can literally eat the insulation systems off of wiring. It can eat rubber, the rubber belts, the belt drive systems on your fans and motors and stuff like that. So anything that's in there has to be UVC protected or UVC proof, right? So loading it up is great for a short-term thing, but you have to take into account that if you don't cover all these other things, your air handler is going to die, right? So UVC is a really great thing to do. Next one, talking about increasing the fresh air amount. So in this particular facility, there were some air handlers that could be set up with a really high amount of fresh air, damper-wise, but they didn't have big enough cooling coils to do it, and they didn't have big enough reheat coils to do it. So the idea was get as much fresh air into the building as you can suck out of the building, because you can't just pump a building full of air. You have to get the air back out of there, right? So the idea is get rid of as much of that recirculated air as you can, exhaust it, but you have to treat that air before you send it out. If you have a COVID-laden air and you exhaust that stuff before you hit it with UV and before you hit it with HEPA, you're going to be creating a nightmare for people on the outside of your facility that may be wandering around, right? So you have to do more than just exhaust it. You have to treat the exhaust stream as well. Again, that was for this particular facility that was going to be loaded up with COVID patients.
Scott, could I ask one other question? I'm sorry to interrupt, but it
certainly.
goes directly to the slide. So in addition to bases, I look at a lot of stuff across universities, right?
Yeah.
And now what we are seeing is, and you may have, don't know the exact regulations that they apply to bases, but the new regulations are coming in terms of educational, other office facilities and public buildings are in terms of the number of exchanges, the number of frequency of exchanges when people are in there versus when people are out there, right? So,
Yep.
so most of the new is, so if the, which means the